Okay, welcome back. So today we're going to finish up Stokes Theorem, and then we're going to move on to the final section of the book, 13.9, that we're going to cover. So if you remember from last time, Stokes Theorem was a way to translate a line integral that encloses a surface into a surface area integral. Now it's calculating the flux of the curl of the vector field. And we also talked about some behaviors between a conservative vector field and Stokes theorem. So if we had some closed line integral and we needed to calculate f dr, if f was a conservative vector field, we found that we could just say that that was 0. Because then we could translate it using Stokes theorem to a surface area integral of the curl of f, which we know because if f is conservative, that's 0. So why don't we start off our example today, kind of illustrating this property. So we're going to find the parameters a, b, and c such that the line integral, closed line integral of c f dot dr is equal to 0 where c is any closed curve and f is our vector field a e to the x plus y squared b times x times y minus z squared sine of y and c z cosine of y. Okay, so this doesn't say anything about saying that f needs to be conservative, but we know that this line integral for any generic closed curve, the only way for this to be 0 for any arbitrary closed curve is that f is a conservative vector field. We learned that last time. So even though it's kind of hidden in here, this is asking, hey, do you know this property? Do you know that you need to prove that f is conservative? Okay, so we need to find a, b, and c such that f is a conservative vector field. So we need f to be conservative. One way for f to be conservative, or to show that it's conservative, is that the curl of f is equal to the 0 vector. So let's go ahead and find the curl. So we have I hat, j hat, and k hat. We have our derivative operators. Then we have a e to the x plus y squared. We have b x times y minus c squared sine y. Oop. Kind of a little bit over. And then cz cosine y. Why don't we move this column over a little bit? Like that. There we go. Okay. So for the x component, we're looking at the determinant of this block here. So first we need to do a partial y of this. So this ends up giving us a negative c times z sine of y. And then I need to take the subtraction of the z derivative here, which gives me plus 2z sine of y. Okay. Then for the j component here, we're looking at the determinant of this block here. And remember, there's also a negative. So why don't we do the off diagonal first? So we do partial z of this thing here. Well, this is just 0. There's no z's that show up in that. And then we have x, partial x of this guy here, but there's also no x's here. So this is again 0. So then finally for the z portion, we have partial x of this thing right here. That just gives us b times y. And then we're subtracting the y derivative of this right here. So we get 2 times y. Okay. So in order for f to be conservative, we need the curl to be the 0 vector. So take a look at this. Well, we have 0 already in this element, but the first element and the third element are non-zero unless we have that what looks like if c is equal to 2, then we get this, that these two terms cancel. And over here, if we get b is equal to 2, that these two terms cancel. So thus, we have that b is equal to 2, c is equal to 2. And is there a constraint on a? Well, we look at this. There's no a's that actually come out in this curl here. So it doesn't matter what a is. As long as we have b is equal to 2 and c is equal to 2, then f is a conservative vector field. So we can say that and a is some number in the reals. So with this, we can say that f is a conservative vector field. And if f is a conservative vector field, the line integral over any closed curve of it is going to be 0 due to Stokes theorem. Cool. All right, so let's do an example of where we actually utilize Stokes theorem, right? Before we proved it, we did an example where we calculated both the left-hand side and the right-hand side and showed that we got the same values. We also talked about if we have certain circumstances, we can actually choose our surface with the same boundary as the surface that we want to calculate. We talked about conservative vector fields and Stokes theorem, but we haven't actually done an example where we might want to actually utilize Stokes theorem here. So let's do, we're going to evaluate the closed line integral of f dot dr where f is the vector field z squared y squared x, and c is the triangle that's created by the points 1, 0, 0, 0, 1, 0, and 0, 0, 1, counterclockwise. Okay. So we could do this line integral, right? What we would have to do is separate the region, the line C into 3 different segments that talk about the line, and we have to find parametric equations for all 3 of those, and then do the line integral on each of those things. We do know that it encloses a surface, however. So what we could do is rather than do 3 separate line integrals, we can use Stokes theorem. So that means we're going to have to do the surface area integral that calculates the flux of the curl. So the plane that connects the triangle's vertices will work for our surface. So then we need to find the plane that shares these 3 points. So this is very much like a problem near the first segment of our class. In fact, if these points were even just a little bit off, it would be really hard to lock down. Or not really hard, but we would have to do the same procedure, right? You would find a vector that connects maybe point A and point B, if that's what we want to call them, and then maybe a point B to point C. And then we would find the normal to that using the cross product. And then we could find, then with the normal, we could write out the equation of the plane, if that rings any bells. But the fact that this is 1 in X and then zeros, and then 1 in Y and then zeros, and then 1 in Z and zeros, it could be intuitively thought of as just being X plus Y plus Z is equal to 1. And there's a few ways that you can arrive at that just intuitively. If you're just plugging in zeros to all the other ones and you're always getting 1, you can kind of imagine there's probably a 1 on this side, and then these have coefficients of 1. The normal is also 1, 1, 1. And if you think about what this looks graphically, you can kind of understand why that normal is 1, 1, 1. But if you can't do that, this is the type of thing that we should practice for maybe an upcoming exam, where, hey, I need to find this plane equation. Okay, so now that we do have the plane equation, we can start to look at doing the surface area integral. Right, so this actually gives us some idea of what our g function needs to be. In fact, we can just choose x plus y plus z, which is equal to 1. Let's also go ahead and calculate the curl of f before we get started. So we have I hat and our x derivative, and then z squared, j hat, partial y derivative of y squared, and then k hat, partial z derivative of x. So our x component is the determinant in this block here. So we do a partial y of x. Well, that's just 0. Then we're subtracting partial z of y squared. Well, that's also just 0. Then we have the negative of the determinant, that's this block here, the outer pieces. So we can look at doing this one first. We have partial z of z squared. So we get 2z. And then we subtract the on diagonal only because we're looking at the y component here. And this is partial x of x, where we just get 1. Then we look at the determinant of the left block. So we have partial x of y squared and partial y of z squared. Well, those are both 0. So we get actually a pretty clean vector that we need to be working with. So using Stokes theorem, the line integral that we were asked to calculate can be instead written as the surface area integral of S with the vector 0, 2z minus 1, 0 dot ds. Okay, and now we can look at the steps to calculating this surface area integral. Step 1. Let's decide on where to project to. This triangle is actually really nice to project to any of the coordinate planes. So let's just arbitrarily pick the xy plane. Which means that our p vector is k hat, moving in the z direction. Okay, now we need to look at the projection onto the xy plane. So we have y and x. So the projection also looks like a triangle. Here we have x is equal to 1. Here we have y is equal to 1. And we can find the equation for this hypotenuse. This is y is equal to 1 minus y. Right? When x is 1, we get 0. And when x is 0, we get 1. We also have to kind of try to keep in mind what the orientation of our line integral was. So this was, I believe, it was counterclockwise in our problem statement up above. Yeah, counterclockwise. So if I'm looking down, so this is out of the screen is positive z, and I still need to be going counterclockwise, then I'm just going to be drawing these arrows here. So now step 3. We look at the gradient of our g. So this was just x plus y plus z. So we get 1, 1, 1. We also need to take a look at the magnitude of the gradient of g. dotted with k hat, because that's what our p vector is. Well, this just grabs the absolute value of 1, so we can just write that as 1. Now we also need to be concerned about the plus or minus, right? On the gradient for these type of vector surface area integrals, we need to look at the plus or minus. So the normal, according to the right-hand rule, so kind of think of your fingers curling counterclockwise on this plane, right? That means that our thumb is pointing in the positive orientation in the z direction, or it's actually pointing in the 1, 1, 1 direction, but it's the positive version of this, right? It's pointed up. So we're going to choose, so the orientation of the surface is determined by the right-hand rule. To be up, or we choose the positive. Okay, so our f dot ds is therefore 0, 2z minus 1, 0, dotted with 1, 1, 1, dA, which ends up giving us 2z minus 1 dA. Okay, we have a question and then we can go to step 4. If we weren't given the counterclockwise information, how would we determine which sign to use? You don't. If there's no orientation given, then you can't translate this to a surface area integral because you do not know if you have to choose the positive or the negative. So if you remember, these line integrals have specific, you start here or end here. So if you end and start at the same location, you still need a direction associated with this. Okay, so for step 4, we need to remove all z's from our possible integrand. So we can say that z is equal to 1 minus x minus y. So our f dot ds therefore becomes, we had this z in here. This will become 1 minus 2x minus 2y dA. Okay, and then we are all ready to set up our surface area integral. I guess I've done a little bit of an oopsie here because I said that f was this thing here, and then I calculated the curl of f, and that's what this should have been. This should have been the curl of f, like that. Because that's what we're trying to calculate. There we go. Just because we called this f up above, but we really needed to look at the curl of f. Okay, so now we translated this into the area integral of d over d, 1 minus 2x minus 2y dA. So our region D was just this, this triangle here. So I'm going to choose to do dy dx, which means that y goes from 0 to 1 minus x, and then goes from 0 to 1. This is the integral from 0 to 1 of y minus 2 x times y minus y squared, evaluated at y is equal to 0, and y is equal to 1 minus x dx. Get the integral from 0 to 1, 1 minus x minus 2 times x minus 1 minus x minus 1 minus x squared dx. So we can FOIL this out, do some simplifying. So I get a x squared here, and then I get another 2x squared here. But this one is positive, and this one ends up being negative. We have double negative, and then we have this one out here. So the highest power that we see on FOILing out is just a 1x squared. For the linear terms, we get a minus 2x, but then it's negative here. And then here we get negative 2x here. And then we just have the x here. So this ends up giving us just an x. And then for the constant terms, we end up with a 1 from here, but we're subtracting it. And then here's this 1 here. So we actually don't have any constant terms, dx. So this is equal to 1/3 x cubed minus 1/2 x squared, evaluated at x equals 0 and x equals 1. The 0 case is really nice, so all I really need to worry about plugging in this 1. That just means we have a 1/3 minus a 1/2, which just gives us a negative 1/6. Okay, so that is one example of when Stokes' theorem could be accurately used, right? We had some line integral, and it was over a line that would have had to be broken up into multiple segments. And whereas we could do that now, it might be a little bit painstaking because we would have to first we'd have to find out what those edges were, parameterize them, and then do line integrals over all three of those things and then add them up. As opposed to, now we could just look at some surface who has a boundary that's represented by the curve C. So we chose a really nice surface. So it's just the plane because all of those line segments happen to be in the same plane. That's very convenient. So then we were able to use Stokes' theorem to kind of translate this into a surface area integral. So not too bad. Okay, so I do have some questions coming in. Can you explain what you use the right-hand rule on? So the right-hand rule determines which direction the normal needs to be pointing in given an orientation or vice versa. So our problem statement said that the orientation for C was counterclockwise. Right? And that's why we also kind of draw the arrows here. So if you go ahead and use the right hand rule, meaning you put the base of your palm on the screen and you curl your fingers in the direction that's happening, right? So you put it down, you can see that the normal should be pointing in a positive Z direction, right? So that means that we're going to choose the positive here. So vice versa, perhaps maybe the problem statement wants you to go to the reverse direction of Stokes to convert the surface area integral that calculates the flux of the curl, and they give you a normal to the surface. Therefore, you know what the orientation of your line integral needs to be, because you point your thumb in the direction of the normal, and then you realize that your fingers curl in the orientation of the line. So it goes hand in hand. It goes vice versa. So if you have some kind of orientation, you can figure out what the normal direction is. And if you have some normal direction, you can find out what the orientation needs to be. So to use Stokes, we'll need an orientation though. Correct. Every line integral will have an orientation because a line integral starts and stops, right? So it has to go from a certain point to another point. So if it starts and stops in the same location, meaning it's a closed curve, we still need an orientation. That's how we've done line integrals. Okay, do we have any last questions? Give you guys a second, because we only have a few minutes left. And maybe it's best that we don't jump into the last section, because we would only barely talk about what's happening. Okay, we have another question coming in. So when it says out is positive, use RHR, I'm guessing that's the right hand rule, to orient your curve. I don't know where you're exactly getting, because you have quotes around out is positive. So yeah, if there's a problem statement that says that, yeah, the surface has a normal that is pointing in a particular direction, that gives you the orientation that your line integral needs to take. If that's what you're doing. If you're using Stokes, then you need this to orient your line integral, right? So I'll just kind of picture where your surface looks like and go ahead and place your thumb in the direction of the normal and then just curl your fingers, and that will give you the idea of clockwise or counterclockwise, the orientation of the line integral. If we have time, could you show a bit more slowly how you know the direction of the projection from the information we have about the plane or more general surface? So here it said that the line integral was counterclockwise. So typically when you say counterclockwise in R3, you think about looking down on the z-axis, or you're looking down on the x via the x-axis or down via the positive y-axis, right? So imagine that you've got this thing sitting in, and it sits in the first quadrant of R3. And if it's going, so let's kind of see if we can draw a picture of this in R3. Okay, so we started So we had all 3 points, 1, 0, this. They're all just 1 up on each coordinate plane, and we're going counterclockwise. That means we're going like this. So when you think about the projection, just keep in mind the orientation that you still have, and then you can figure out what the normal is. So think about, if you look at the surface here, if you curl your fingers, right, in the direction of this orientation, right, it looks like my thumb is pointed out of the screen. Maybe it's pointed out like, maybe like that. So that just gives you an idea of the positive or negative of the normal. And we already said that the normal, because the gradient of G was 1, 1, 1. So we knew that it was either 1, 1, 1 or negative 1, negative 1, negative 1. So that's what the options for the normal was, based off of the gradient of G. But because of the right-hand rule and the orientation of this curve, we know that we point out, right, in kind of in our direction, rather than into the screen. Okay, why don't we take our 5-minute break here then? I'm sure that the TAs will be on in just a second, and then we can jump into whatever they've got planned for you today. So then the plan for tomorrow is we're probably going to finish up with the divergence theorem, or Gauss's theorem, which is 13.9. And then we might have a little bit of extra time, either at the end of class or pretty much on Thursday, we'll have some extra time. So if you guys have any specific material that you want me to review or kind of go in depth, or you just want to make it an open lecture where you can try to ask me questions, I can't guarantee that I'll have good examples if you do it that way. Or you could just, send me, oh, can you explain this a little bit more? And I can try to see if I can find some examples like that. Otherwise, I have some old questions that don't appear in the exam archive that I can see if I can dust off, in case I don't get any contact about what kind of stuff we should do. Okay, yeah. So can you review flux? When you are talking about flux, are you talking about flux through a surface or flux through a line? Or is that what you're confused about?